Hello, can you hear me, please? Hello?
Yes, doctor.
Okay, Bismillah Rahman Rahim. Let's start now, please, where we'll do the last topic today, error in solving the linear system. And of course, this will not come in the midterm exam. Midterm exam will be before this topic, which is the iterative method, which we already finished last time. You remember that one here, we are solving the linear system and we are using numerical method, and generally we are getting the approximate solution. And when you're getting the approximate solution, even if your approximate solution is very, very good, it's still some, sorry, still some there is error, because exact and approximate, they are never equal each other, right? Never equal. Now, in this case, we will say there will be some other source, the error will be increased. The error will be increased, even if you use a very good method here. And for this one, we have to check now about the conditioning of the system. Conditioning of the linear system. Linear system. Now the conditioning, when I say the conditioning of the linear system, what does that mean? You know what they mean, the condition. Condition mean good or not good, right? So we can say the first is well conditioned. And the second one we say is not well, which we call ill. Ill means sick, right? Is called ill condition. Now, in this case, yeah, basically when we solve the system up to now, what we check? Up to now, we check our system should be non-singular, and then we find the unique solution. Non-singular system condition only give you idea you have the unique solution, but non-singular never give you idea that you have the good unique solution or not here. So here what we have to discuss that one here, where our given system must be the non-singular again, but we have to check extra condition, and that condition is called the conditioning of the system. And we have to check our conditioning of the system. If our condition is well-conditioned system, and well-conditioned system mean you will solve the linear system by using any method, you have a small error, not big error. But if your system is ill condition, if your system is ill condition, whatever method you use, you will never have a small error, you will have a very big error. It's not the fault of the numerical method, it's fault of the system. Your system is ill. So generally what we say, if our system is ill, no need to solve it here, because if we solve the ill conditioned system, we will get a very, very big error. We will get a very big error. That's the things we will discuss, inshallah, in the last topic of chapter number 3 we have. Now let's start that one here. Let's say define you one of the best vector we have here, which help us in this regard, and that call is a residual vector we have here now. Residual vector is what? It is I denoted by R, and the formula for this one is B minus AX star. B always given by the teacher, A always given by the teacher, and teacher also provide you X star. What is X star? X star is an approximate solution, computed solution. Computed solution mean you use some numerical method and to find out the approximation of what? X star is the approximation of this exact solution X we have here now. If you can look for the, what is your exact system? Your exact linear system is what? Your exact linear system is is what? A x is equal to what? The B. A given by the teacher, B given by the teacher, and we look for approximation of this one, x. And what is x here? Is exact solution. We look for the approximation, and approximation solution, let's say denoted by x star here. Now, if you can write this system, you can also write this system that B minus ax, this is equal to what? This is equal to 0 because I take ax on the other side and we can have here this one. Now you can see here, what is your R? I define here. R is equal to what? B minus A x star. B minus A x star. Can any student help me and tell B is exactly the same we have here? Minus, A is A, and this is exact, and this is approximate. And of course, when we find the approximation, we always find we look for the best approximation. Can you tell me what will be the value of R should be from here, looking for this information? What will be the value of R? Should be. If you can see here.
Similar to the first one. If it is similar to the first one, it's better.
Yes, is it similar to that one? Of course, not equal, because this definitely, this will give you the jawab 0. Because why give you the jawab 0? Because this is the exact. And this is not exact. It's mean this will be what? Approximate to the 0, means close to 0. It means R must be very small vector. Small vector means the element or the value of the or element of the vector R are very, very small. This makes sense, right? By this formula we have. And when your R is small, it means this is very close to X. That means when I say R is small, we talk always in the norm way, that this norm should be this small. When R is small, it means the difference between exact and approximate should be small. This makes sense, right? X, exact solution, and X star, approximation. And this norm should be what? Small. If this happen, this should be happen. But if this happen, then it means you are playing with or you are solving the well-conditioned system. You are solving the well-conditioned system. Sometimes we also face some linear system like this one, when your R is small, but your error is very, very big. So when your error is big, it means this is not possible here, or logically is not true here. But this happens in millions of the linear system. When your R norm is small, but your error is a big, this only happens if your system is ill-conditioned system. That's the thing, that's the story. How can you check your system is small or your system is a well-conditioned or ill-conditioned? By definition, let's I give you the example. Before I give you the example, there is the residual vector is this one, and relative residual we can define by this form. Let's see by the B. Now let's take the example. I took this example here now. And your A given, your B given, and teacher also given. The solution of this linear system, approximate solution of this system is 3 and 0. And you can check, it look very nice. When we put x1 is 3, x2 is 0, what is the jawab? 3, alhamdulillah, left, right, equal. When we put 3, 0 in the second equation, we have 3.003, this is 0, and 3.003 is a very good approximation of 3.001. It means this is look nice example here. And when we find the R, and R formula, I already give you what is the formula of R. R is equal to B minus AX star. B is your right hand side, A is your 1, this 2, 2, like this one. You multiplication with that by this formula. When you use exactly this value, you will get R. And you can see what is the L infinity norm of this vector. L infinity norm mean the maximum element in absolute sense, and which is equal to this one, absolute sense. And this, alhamdulillah, this show is a very small r here. It means your error should be the small here. Now we look for the exact solution for this one, and exact solution for this system is 1, 1. You can put here 1 and 1, so 3, 1 and 1, exactly the same. This is the exact solution, which you can find by yourself because you can find the value of x1 from the first equation, put in that one, and you can have. Now you can see what is the difference between x minus x star. Your x is 1, 1, and x star is 3, 0. So you have 1 minus 3 and 1 minus 0. So minus 2 and 0. What is the maximum? Is 2. An error equal to 2 is a very big error we have here now, because the error should be close to 0, but it is not. Why this happen? It's mean this given system which we are talking about, this system is ill-conditioned system. We use the best method to find x star approximate solution, but in the end we find R is a small, but error is very, very big. It means it's not wrong with the method, it's wrong with the system. That means that system is ill-conditioned. Remember, I told you if your system is an ill-conditioned system, no need to solve it, but I solve it here. So it means here we need some condition to check your system is ill or the well system. Let's we discuss now here how to find out ill conditioning system. And there are many rules to check system is ill condition or well here. As I told you, the first condition we finish, but that condition when we solve the system, and then we know that our system is ill. And what is the condition here? If the norm of R is a small, then the error should be small. But R is small, but error is a very big one we have. It means something is wrong, and the wrong is a system is ill condition. Now we can have here now. Also, there is another way to check your system is ill condition or the well condition. And I give here now. This is your system, right? And when you solve this system, this is very simple system. You can easily solve that system. When I solve this system, I will get the approximate solution I got here is this one. Okay, you will get inshallah when you solve it. Now, what I did now, I make a small change in the system. In place of 0.3, I use 0.33. No other, the coefficient and the right hand side change, exactly the same. Only I make very small change in this. And when I make small change in this one, we have a big change in the solution, you can see. Because here 0.1 and 1.3, now we change 0.3 to 0.33, which is a 0.1 change we have. And we have a big change in the solution. This is another way to check our system is ill conditioned. That means you make a small change in the A matrix and you have a big change in the solution. Let's say also I take another one here now. I make it now very, very small here. It's a 0.333. And now you can see the jawab completely changed here. Big answer, a big difference between the previous answer. It means this type of the system, we can say it is ill condition. So what is the second ill conditioning condition? You can check. And second way to check your system is ill condition. Or if you make small change in the coefficient matrix, if your change in the solution is small, then it means your system is well. But if you make small in the coefficient matrix, you can have a big change in the solution. It means something wrong with the system, not with the method. And the wrong with the system is it is ill-conditioned system. And the same thing we can have here now. If you can make small change in the right-hand side, and if the change in the jawab, the answer is a very small, we say well-conditioned, or if you have a big change in the answer, then you say ill-conditioned, or you can change some number in the A and some number in the B, and you have a big change. This is the way. I give this example here like that. Now what we need here is a very simple condition to check our system is ill or well without solving it. Up to now, whatever the condition I gave, I solve the system here. Now it's a useless to solve the ill conditioned system. Before we solve the system, we have to check the conditioning of the system without solving. And this is one of the simplest condition we have, which we call the definition of the condition number of a matrix. And how can we define the condition number of a matrix? This is the formula we have. The condition number of a matrix always equal to the norm of A into the norm of A inverse. And the value of K of A, if you can check from this formula, the value of K of A always greater than equal to 1. You will never get any value of K of A is less than 1. Of course, no chance less than 0 because we are talking about norm. Norm is always positive. So condition number of A is always greater or equal to 1. And that's the range we can have here. Now we can approach to the infinity here. Now, if we can see here, if we can have here, we say the condition now with that one, if value of the K of A, I say the value of K of A always greater or equal to 1, right? And if the value of K of A is close to 1, if the value of K of A is close to 1, it means your A is well conditioned. Your A is the well conditioned matrix. Now, here a student asks me, when we say close to 1, what number we can fix it? We cannot fix it, please here. This formula is very simple, and I told you simple thing is not give you the proper requirement here. Here we can say if the value of K of A is a 4, 5, 6, something like is okay. But has the value of K of A, if K of A is bigger than the 1, that means very away from 1, then something wrong, and the wrong is your matrix A is ill conditioned. Your matrix is ill conditioned matrix, and if your matrix is ill conditioned and matrix included in the system, your system become ill. This is I mentioned here that your A is a well-behaved mean well-conditioned if the value of K of A is close to 1. But if It is increasing to the ill conditioning when value of k is significantly greater than 1, where we have coming closer and to the infinity. For example, I say, check this matrix is the ill condition or the well condition. So we have A is this one. We can easily find out the inverse of the matrix. And when we have the inverse of the matrix, we can easily find out the norm, and norm of the matrix. We are using L infinity norm. And you remember, I give you the definition of the norm. L infinite norm of a matrix is what? The sum of the element in absolute sense of first row, then we check second row, and then maximum. What is the first row? 3. And what is the second row? 5.9. It means what is your L infinity norm of A? Is a 5.9. And this you can check here now, please. No, this is not 0.4 here now. So we have is what? You have 2000. We have 5009, not 0.4, please, should be cancelled. Is there 5099, now 5999, and this is how much? 300. So what is the maximum? 599, which is this one here. And when you multiply that one here, inshallah, you will get that one. And that is a close to 1. No, it's a very big one. It means something wrong with that one here. This matrix is the ill condition matrix. I take another also the matrix. We have, this is A and this is, we can find A. And when we find the inverse of this, the conditioning number of this matrix, you can see what is the norm of A is a 5. And what is the norm of A inverse? Also 5. So 25, even 25 is a very big value here now. This is the ill conditioning things we have here now. So that's where we will check here. I give many examples for this case here now. And you can easily check that one here. I give some one time in the exam is this, and the student confused. And what I said, I say if the condition number of a following matrix is 8.88, this what? Find the L infinity norm of the matrix. So what a student did, they find the inverse of that one here. No, you don't need to find inverse. Directly use the definition. What is the condition number of a matrix is this one. Okay. So now what you have to do, can you please close, anyone please close your Saud. Please close your mic, please. Okay, Saud, close your mic, please. Now we can have here now K of A is given what? By the teacher. K of A is given this one. So only you have to calculate what? The norm of A. And the norm of A you can easily find out from this one here, which is a maximum one. It is 21.1. Now, teacher asks you to find L infinity norm of this one. So we can take this one in the denominator and you can find the norm of A is this one. But when I give this problem in the exam, what a student did, they use some method to find the inverse. It means they waste their time here. No need to do this one because we simply have to use this file. Okay, plus I give you the last point in that topic is called the error in solving the system. That's I give you. And now I give you this is the error in solving the linear system when teacher provide you X star and he say find the error in the linear system. This formula you have to use. R into A inverse. R, you know what is the formula of R? R is equal to what? A, B minus A star. B given, A given, X star also given. And then you find only the inverse of A, then find its norm here. But in exam, teacher never asks, generally never asks you this simple error. He always asks you this error. Find the relative error in the linear system. And that's the formula we have to use it here, please. That's the formula we have to use. That K of A, we know what is the condition of the K of A. Condition K of A is a condition number of a matrix, and this formula is norm of A into the norm of A inverse into R. You know also the norm here and the B here. No need for the proof because not. Let's we do many times. I give this example in the exam here now, please. Very good example. He say find the condition number of the following matrix with an is equal to this one, and condition on n is what? N must be start from 2, 3, like this one here. Now you do what? Do the first part, this one. This is the second part. We come second part later on. Find the condition number of the following matrix. And we know what is the condition number of a matrix, please. We already know the formula. Condition number of a matrix is what? K of A equal to what? Norm of A and norm of A inverse, right? A given by the teacher directly here, and you can find easily the inverse. I will tell you here. Can any student give me idea, please? What is the norm of A? Any student? What is the norm of A? L infinite norm of A?
2.
Is it 2? Because what is the first row? 1 plus 1, 2. And what is this row? 1, this one. What is your n? Start from 2. So if you take 2 here, it becomes half. So 1 plus half is 1.5. So what is the maximum? Is it 2 we have here? So our norm is the 2. So this is, alhamdulillah, we get what? 2. So now we need to find first A inverse, then we find this inverse now. Now you know how to find A inverse. This is 2 by 2 matrix. We take determinant of this. 1 over determinant, sorry. 1 over determinant. What is the determinant? The diagonal multiplication, which is this one. And then you change the position, right? And change the sign of this diagonal. So we have this one. And when you simplify, you have, inshallah, you get, this is. Can any student now give me, different from the first one who give me the answer for 2, please? Don't give him the answer now. There, let me check the other student. What is the norm of A inverse now? Any other student, please? What is the norm of A inverse? And you know what is the norm mean, L infinity norm, which means the maximum of the row, sum of the element of each row, then we can say maximum of the row. Which row is the maximum, the first one and the second one?
I think the first one and the maximum is 1.
Allah is one. Allah is one. Eh? You see, you put simple n is 2. Let's check with 2. When you put 2 here, what you got, please?
I've got 1.
Minus 1, right?
Yeah.
And this is 2. So we don't care minus 1. So we have 1 plus 1. How much?
2.
1. Sorry, this is 1 and this is 2. So what we have the first row, 3, right?
Yeah.
When you put 2 here, what you get? When you put, we are putting n 2 here, we are get 3 in the first row. When we put 2 in this row, what we'll get?
We got 0.
We use what? We use 2 here. We have 2 minus 2, right?
Yeah.
And then we find the L in the absolute sense. So 2 plus 2, how much? 4. This give you 3. This give you 4. Which one is the maximum? this row.
The second one and 4.
The second one. And the second one is what? What is the A inverse norm? A inverse norm is 2n. 1n plus this, n is a 2n. This is the maximum than this one here. That I give here. And then we find out here what is the K of A here. And K of A is 4n. And of course, about the conditioning you say here, has your n approached to infinity, you are approaching to the ill conditioning matrix here. Right? This we show that the matrix is ill conditioning when your n is very big one here. Because if n is 100, so your K of A is a 400, which is a very big one. But if n is 1, alhamdulillah, we can say if n is equal to 1, then K of A equal to what? 4. And 4 is not very far away from the 1. So we can say the well-conditioned matrix. Now come to the second part. The second part, he say, if n is equal to 2, we choose here. And this is approximate solution is given. This is the right-hand side, the system also. Now I give the right-hand side here. And he say, find the relative error. So relative error formula is what? Is this one. So we already find out what is K A, which is 2, I think 4n, right? We have already find 4n. Now you are putting n is equal to 2. So what is K of A is 8. Now we need to find out the R norm. Can you give me, any student, what is the B norm? What is the B norm, please? This is your B. What is the B norm? Oh, yeah, Allah, it's basic things, wallah.
1.
Is a 1, is a 1, because the maximum element in absolute sense. This online class should, Allah, finish this online class. The student become worse and worse, wallah. Now, when we're taking the R and R, this is a formula for to find out, and we have B given by the teacher minus A2, you put n is equal to, now this is n is equal to 2, so 1, 1, 1, and 1 is half here. You can have here. Now this is the things we have, and this is X star. X star is provided by the teacher is this one. And when you simplify this one, you will get this value. Which one is the maximum? And the maximum is 0.005. So you have K of A is 8. And R, you just find out this. B norm, you find out this one. And this is the error. An error is not very bad. It's a 0.0. So it's close to 0 here. It means even if you have n is 8, you will have a small error. It means 8, we can say the well-conditioned that one. But if the is 8 is smaller than 4 or 5, we have a more smaller error. Let's take the last example for this chapter. And this is called, same example I used, the same example but the only difference is this is given 3 by 3 now here. So first you have to find what is your A, 1, 1, minus 2, 1, 2, 1, minus 1, minus 2, and 1. So this is your A. And you have to find the inverse. But one thing, remember that one, please. In exam, if teacher give you system for checking ill condition, he generally give you 2 by 2 system. But if he give you 3 by 3 system, teacher generally provide you what? A inverse by himself, right? But if the system is 2 by 2, he will not provide you the inverse, you have, because 2 by 2 inverse, you can easily find out here now. Now, you can see what is the L infinity norm of A, the maximum row, which is a 5, second one. And what is the maximum row in this case? I think is the last one. 2.5, 1.54, 4.5. Yes, this is the last one. And then you can have here now, what is the value of K of A? Is 22.5. So 22.5 is slightly away from 1. So we can say our system is the ill-conditioned system. Now, go for the second part. He say find the, if x is equal to this one, find the vector R and its L infinity norm. We know what is the formula of R. It is this one. You are given B, which is the right hand side. You are given A, coefficient matrix, and you are provided also the approximate solution by the teacher, which is this one. And then you multiply this one. You have the value of R is this one. So what is the maximum of element in absolute sum? It is this. Now the last part, he say compute the relative error, and relative error formula is K of A is R norm, and the K of A we just find 22.5, which is this one. R norm we just find out 0.07. And what is the, this is B. What is the norm of B? Is a 1. And 1.57 is not close to 1. It's a big. Why we have it this big? Because your system, we already checked in the first part, our system is ill-conditioned system, and ill-conditioned system never give you the good error we have here now. That's the things we have here. Any question, please? This is same example here. And no, because this topic is not with us. So leave that one here now. So this is a story of the chapter number 3. In chapter number 3, what was the things first we have? I just give you the introduction of the system. I give you that how can we have a system, simultaneous system, and what is the meaning of the non-homogeneous system, what is the meaning of the non-singular system. And then second things, if you remember, I give you what? Some special matrix which help us. Special matrices. Then number 3, I give you what? Direct method for solving the linear system, which we use to direct method, gas elimination and LU decomposition. The gas elimination by we did by two version. One is a simple gas elimination, another is partial pivoting. And then we did the second direct method, LU decomposition, which also have a 2 version, Dolittle and the Crotts method. Then number 4 topic of that chapter, it was iterative method. In iterative method, we discussed 2 cases, 2 methods, Jacobi method and the Gauss-Seidel method. And the last topic of chapter number 3 was error in solving the linear system. An error in solving the linear system, basically what we check conditioning of the system. If your system is a ill-conditioned system, you have a big error, and if you have a well-conditioned system, you have a small error. This is the story of the chapter number 2 and 3. We already finished the big chapter of our syllabus. We left with the last 3 chapters. We left, I think, here. Chapter 4, 5, and 6 we have to do. As I told you, chapter 6 is a very simple one. We can finish in 1 lecture or 2 lectures maximum. Any question you have for this case?
Okay.
Is okay, right? But as I told you, for your material for the midterm exam, is chapter number 2 and up to chapter number 3, up to the 4th topic, not 5 topic is coming in the exam we have here now. We will talk, inshallah, the next chapter. Maybe you already know from this one, chapter number, I think it's chapter number 3. No, sorry, not this one. Chapter number 4, sorry. This is the thing, sorry. We have to start the chapter number 4. And this is your next chapter. Maybe you already have the idea of interpolation in your courses. Any student have the idea of interpolation or not? No.
Yes, kind of so.
Yes, that's the things we have to use here. What is our topic of what you call it? Chapter number 2, we find the approximate solution of the nonlinear equation, right? If you know the chapter number 2, what we do, we find approximate solution of nonlinear equation, which is what? Nonlinear equation I denoted by f of x is equal to 0. And what was the chapter number 3? Chapter number 3, we find approximate solution of linear system, which is this one. We find approximate solution or root, and we find solution of the system. What we have to do in chapter number 4, the basic things we find approximation of function. We find approximation of the function we call it f of x at given point x. For example, what is given here now? You are given the table and you are given value of x, say 1, 4, 8, 12 something value. This is the x value and the corresponding value of f of x. This is also given. This is also given. Let's say this is 5, 7, take any value, right? And let's say 9, let's say 11 here. This is given information to us. Who give us this one? Someone give us, but he never give the formula, how he calculate the value of f of x at this point. This you did by some experimental work, some, what you call it, the survey, some survey, they give this one here. Now, the job of numerical man will start here. And he says, he asks someone, please, can you help me to find what will be the value of f of x at value of f of x at the 3. What is the value of f of x at 3? That's the numerical man will be do what? He use a table, given table, and he create the formula, approximate formula for that table. And when you have the formula, you can find whatever we have to find the value of the function at any point we can have inside the given interval. That's the things we have here now. We call two way to deal with the interpolation and the extrapolation. And in extrapolation interpolation mean you are looking for the value of the function within the range. Range is your what? 1 to 12. Any point inside the range. This is called interpolation. And extrapolation, if you're looking for the approximation of the function outside the range here, this extrapolation. And we will not discuss the extrapolation. We will do only the interpolation. And as I told you, the interpolation is what? Interpolation mean find the approximation of the function at a point which must be measured inside the range. Range is your 1 to 12. This is the most important thing that here a student can make a mistake here. So you have to, and also remember that one interpolation can be possible many ways. What we use the simplest way, which we call the polynomial interpolation. And the other things also, interpolation, your data point, this data point, when I say data point, I mean the x value. And data point may be equally spaced, may be unequally spaced. This is unequally spaced because the difference between 1 and 3 is 2, difference between 3 and 4 is 1, difference between 4 and 8 is 4. So this is the unequally spaced, but equally spaced means we can have 1, 2, 3, 4 like this one here. So data point may be equally spaced, may be unequally spaced here, but we will not care about, because inshallah we will use two numerical formula. One is called the Lagrange interpolation formula. Another is called the Newton divided difference interpolation formula. And these two formulas said we don't care about the data point. Data point may be equally spaced or unequally spaced. Right? We continue inshallah this one on the next lecture. Any question you have, please?